Hi there, my name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. A while back in ECE2026 Introduction to Signal Processing, we looked at continuous time Fourier series. In this lecture, we'll look at discrete time Fourier series. Now, when people say discrete time Fourier series, they mean the same thing as discrete Fourier series. This is extremely confusing because when people talk about the discrete time Fourier transform, well, that's something related to but distinct from the discrete Fourier transform. Yeah, it's all very confusing. You just got to get used to it. In this lecture, we'll talk about how the DFS, also called the DTFS, relates to the DFT. Okay, enough alphabet soup. Remember that the idea of a Fourier series for continuous time signals was that we could write periodic signals as a possibly infinite sum of complex sinusoids, where those sinusoids all have frequencies that are integer multiples of some fundamental frequency. Now, it turns out we don't need to do a whole lot of work to translate this concept over to discrete time signals, since we've already seen a way of writing a periodic discrete time signal as a sum of complex sinusoids. It's the inverse discrete time Fourier transform. So here's the discrete Fourier transform. Here's the inverse discrete Fourier transform. If I were to let AK equal 1 over n times the discrete Fourier transform component xk, well, then I have this form. So AK are my discrete Fourier coefficients. Okay, we're done. Just kidding. There's more to talk about. Remember that for the continuous time Fourier series, it's possible that you might need an infinite number of sinusoids. And all of those exponentials are periodic with the same period. Now, when we apply that same logic to the discrete time case, we see that there's really only n possible exponentials. So we don't need to worry about infinite series in the discrete time case. Now, let's think about sampling a continuous time periodic signal. We can represent that with a Fourier series like this. Now, when we sample the signal, this infinity here might get us into trouble. We need to band limit our signal. So what we'll do is we'll truncate the series to go from minus m to m, and we'll say that our sample rate needs to be strictly greater than twice the highest frequency in the signal, which is going to be m times f naught. Mf naught is the Nyquist rate for this signal. Now let's sample that band-limited signal. When we sample the signal, we replace t with n over fs, the sample rate. Now, in addition, let's suppose we chose our sample rate so it was equal to n times the fundamental frequency. If we plug in f naught in for fs, this will suddenly look familiar. So we have a band-limited continuous time signal. We've very carefully chosen our sample rate so the discrete time sampled sequence is also periodic. And we wind up with something that's equivalent to the discrete time Fourier series formula we had because of the way that the coefficients wrap around. And we can find those coefficients a sub k by noting that this formula looks really close to the inverse discrete Fourier transform if we just let ak equals x of k divided by n. So the discrete Fourier transform is a conceptual cousin of the Fourier series analysis integral, although we have to divide by n here, and that division by n plays the same kind of normalizing role as the division by the period t0 does in the continuous time Fourier analysis integral. Let's look at an example where capital N equals 8, and I'm given these Fourier series coefficients, where k is specified as going from 0 to 7. Now, if I were to take that sum and just write it out directly, it would look something like this. But this isn't a very intuitive way to think about what's happening. Remember that the DFS coefficients are periodic. So here I have A0, here I have A1, but I can think of this as A minus 1 instead of A7. Here I have A2. I can think of this as A minus 2 instead of A6. So if we think about this A6 term as being an A minus 2 term, and this A7 term as being an A minus 1 term, we can see that we can use the inverse Euler's formula for cosine and combine these terms to form this cosine here. And then we could combine these two terms to form this cosine here. And then, of course, I have a DC term sitting in front. In musical instruments such as the synclavier, the Oscar, and for that matter, the Hammond organ, you specify waveforms by specifying their Fourier series coefficients.